Hey guys, welcome to another video. So today we continue on with the complex number vectors topic in the extension 2 syllabus. If you haven't already checked out the last video on it, please do so. Sets the framework. So today I'm not going to really cover much theory. We're just going to dive in, and if we need theory in the question to be applied, I'll bring it up. So also, if you haven't already done so, please subscribe to the channel, like the videos, and tell your friends. Let's get started. So today we're just going to explore some, I guess, more, I'd say harder is probably the unfair word, just more involved, right? Much more working out, that's for sure, relating to vectors in the complex numbers topic. So let's get started. So first question is from the HSC 2013. All right, what do we have here? Argon diagram shows W and Z, okay, with these arguments. Yep, okay, everything's in the diagram. Oh, wait. Area of the triangle formed. So, okay, area, right, is A. Okay, that's where this A is. Got it. So, we're dealing with area of a triangle. Now, there is, I guess, one formula we know that uses area, right? Area in trigonometry, because that's non-right angle, will be what, a half. Now, I don't know what formula. Some teachers say AB sine C. Some teachers say BC sine A. I use that one, right? Where A is the angle in between, that's angle A there, right? So in this question here, what do we have? So now, in terms of sides, that one there is definitely the magnitude, or sorry, the modulus, right? We're doing 4-unit complex numbers, so modulus, that's modulus as well, right? And that's the angle in between. No, that's not the angle. That's a big angle. So the angle in between here, see the angle that I want is big minus small, so theta minus phi, right? Looking like that. So therefore, using this formula, the area A equals to a half BC, so the two sides there, so modulus Z, modulus W, and then sine of theta minus phi, right? Let's write that a bit better. Yep, now that I got that, I need to connect everything, right? So let's see what I have to prove. I have to prove that this left-hand side equals the right-hand side. Now, I got the A in there, so I'm probably going to sub this piece of information, right, into here later, right? So maybe I'll start with the left and see where it takes me. Yeah? Let's start with the left. So the left-hand side equals to Z conjugate of W minus W conjugate of Z. Now, let's get my tools here, right? Because I know, what do I know? In terms of mod arg, right? Let's list out my facts. So I know that Z has a modulus of Z and a argument of theta, right? Which makes its conjugate have the same modulus, but it's going to be cis minus theta, right? And W, right, or has W cis phi, or conjugate, same modulus, and oops, cis not cos, negative phi, right? All right, let's sub those in, and I reckon I'm going to use like compound angles or something. So let's see. So do I know anything else? No, I don't think so. Right, don't think so. So let's see. So this guy cis theta, this guy cis minus theta. Move that over, need a bit of horizontal space. Minus W cis, sorry, that's phi, isn't it? Because it's W, right? And then Z cis negative theta. All right. Now it looks like, guys, I can factorize out the moduli, all right? So take out Z and W, and what's left here is cis minus cis. Oops. Now I wonder how comfortable are you guys with me combining this? Just remember, right, for each one of these, right, do a formula P. We know that cis of alpha times cis of beta, right, we can combine them by adding, right? Yeah, the angles get added, right? So using this premise, right, we're going to basically combine these two guys. So that gives me what? Cis, that plus that. So theta plus negative minus cis phi minus theta, right? And then last but not least, well, not last but not least, but just to make sure we're all on the same page, you guys, are you okay with, okay, that's cis, that's fine. Now this guy here, it's the same angle, right? It's the same angle, but it's reversed. So that's like negative, right? So are you guys okay where cis negative that? So I guess what I'm trying to say is, you know what? Let's not be lazy. I'll just expand it. I was going to just use the flipping of that and then make the imaginary part negative, but let me just show you full working out for it. So if I use the cos theta minus phi plus I sine theta minus phi and minus brackety cos phi minus theta minus also plus I sine phi minus theta. Now guys, are you okay, right? Cos of any negative angle equals to the positive, right? It's in the fourth quadrant, and sine of any negative angle, that's negative sign, right? Because this guy and this guy will be the same, right? Because it's negative of that guy. And here, right, this guy here will be negative sine theta minus that if I reverse the order, right? So then it'll be I sine this guy minus I sine that guy. So what I end up getting is this. Now let's see, yep, and times two of these. I put it times there, 2I sine theta minus that. Right. Perfect. So that's the left-hand side now. Does it look very similar to what I have here? Sort of, right? So it feels like, now if I sort of then said equals 2, so this one's 4I times that, perfect, okay. So if I go equals to, take the 2I out, this guy, sine theta minus that. And if I take out a half, sorry, no, I'll take out 4I, right? Force factorize 4I out. Then there'll be a half this, that. So guys, just algebra, right? And then I know that this guy here is A, right? Subbing A there. Because it's 4I, capital A, which is right inside. Done. Yeah. So in this one, it's all about just working with what you're given. So if they tell you area, you really don't have a lot of area formulas at a non-right angle. The trigonometry one there is a good starter. And then you're just basically using a few boxes of theory here. The first one being the product of cis. You can add the angles or the arguments and just remember your negative angles, right? In the fourth quadrant, cos is positive, sine is negative. Boom, there you have it. Next question. Now, next question is very common. I've seen it at a few schools. Sometimes I ask a different way. So this, if you look at, I think North Sydney boys had it as well, or North Sydney girls, I forgot which one it was, but also in 2020, Sydney girls had one, same diagram, slightly different question, same concept, right? Same concept. So let's deal with this one. Maybe, you know what? Same concept. Maybe I'll deal with the, I might want to deal with the 2020 version, if that's okay. So I think it's just a better question. Yeah, more recent. I like to deal with more recent ones. So let's deal with, here you go, right? Very similar diagrams. Sydney girls 2020, same question. Let's see how we go, right? Or same type of question. Let's see how we go. So 5 marks. What are we given? So first part, triangle that. Yep, so everything there is in the diagram. Whenever I read these questions, I'm just going to make sure that there's nothing in the paragraph of text that isn't in the diagram, right? Because sometimes you might leave a fact out. So point A and B, ZW, okay, that's a, and M is a midpoint. Okay, cool. Yep, everything's there. explain why. So we need to prove that MP, where's MP? That's this guy here, right? Equals to this. Okay, I think that's pretty easy. Just Sokotoa. Show that vector now. Okay, that's pretty easy. And that's 45 degrees. Find P. Okay, cool. It's very similar to the other question then. Yeah. So let's have a crack at this. Part I. I think part I, we just use Sokotoa, right? So I have this side here, right? And I have theta here, right? It's telling me, show that MP now half of this. So I know, right? W minus Z as a vector, just to be absolutely clear, right? And I'll label it on this diagram here. WZ is basically a vector that goes from here, right? Because AB on the diagram would equal to W minus Z, right? As a vector. Why is that important? Because MB then, because it's a midpoint and it's given, this guy here would be half the length of AB, right? Which is the magnitude of that vector, right? Yeah, because the length of that guy would be the vector, right? Yeah, and this is half. And then MP is what I want. So just Sokotoa 10 alpha equals to opposite over, maybe I'll just label it as MB. Yeah, and then I'll sub it in. So MP divided by a half modulus of W minus Z. Therefore, right, times that guy up, MP. It's just one mark, right? Yep. Half modulus 10 alpha. Boom. One mark. How's that? Not too bad. Now, that was Sokotoa using the lengths. Now I think we're going to use vectors. Show that MP, right? So maybe I'll delete this first. Just the highlighting, I mean. And then maybe I'll introduce a different color. So they want, oops, they want MP going this way, right? So just because we found that, okay. So that MP is a half. Now, can you see that? And I'll try to identify this using underline. A half W that is exactly the same or similar to this guy here, right? Yeah, very similar. So what's this trying to say? Part one said that MP is equal to this guy, but with like some sort of scalar, right? Yeah. So the green is smaller or bigger, smaller in this case, than the pink by a factor of a half times tan theta, because W minus Z is the pink, right? Yeah, W minus Z is the pink, the green is MP. So that's a scalar. So remember, there was a piece of theory where if you had a vector and there was one other vector, that was W, so Z, then that was W, and this is theta, right? Remember, to get W, it's not only cis, so it's Z times cis theta. Sorry, let me write that better. So it's not only cis theta times Z, but if this was K lengths bigger, you put a K there, right? That's a scalar multiple, right? We're going to use that concept here. And the reason why it's important is if I moved, right? See how it's right angle. If I move the green over here, right? Same thing. Then really I can say, right? In this diagram here, MP, which was the green, should be whatever AB is, right? Which is the pink. And then I'm just going to multiply by K cis theta, right? Now, that makes it interesting because in this case here, theta is 90 degrees, right? It's a 90-degree rotation anti-clockwise, right? So we know that if it's 90, cis 90 is I, so that's I, right? So let me just label that, this guy. That's I, right? And what else do I know? I know that this guy, let's see, he's pink because it was pink. This guy is W minus Z, right? So I'm just gonna bracket there. That times. And what's K in this case? K is the scalar multiple there, right? Half tan theta. So let me zoom in if you can't read that. So a half, let me write that again, actually, a bit small. Half tan theta is a scalar multiple that gets us the size. That times a rotation times a vector gives me my final answer, therefore, right, MP as a vector equals, how do they want me to label it? Half I, yeah, perfect. So a half I vector tan alpha, done. Yeah, so it's an I rotation and then multiplied by the blue part, which is the scalar multiple, right? It changes the length of the vector. Last but not least, what's this question saying? If alpha is 45 degrees, right? 45 degrees, let's see, let me put this back over here, right? Put this back over here. So if alpha is 45 degrees, isosceles triangle, don't know whether that has anything to do with anything, right? Who just gives me the value of MP. Then find the vector representation of P. Now, there's a few ways to do this. I always like to do, so pink. So if I was to, actually, no, pink's fine. I found black in MP, so MP here, right, is what I found in part 1. Can you see that that black line, that black vector is the same as this one, right? So this is what I'm going to do. I'm going to use some colors, right? I'll use yellow. I'm going to use yellow. Yeah, guys. So can you see yellow, AP, right? Yellow equals to this black plus this green, and that black is the same as that black, right? So using my vector, resolving vectors there, right? I've got a black vector that looks like this. I've got a big yellow one that looks like that. And I've got a green one that looks like that, right? I've got black, I've got green, and I'm finding yellow, but yellow, just to be absolutely clear, yellow represents a P vector, right? And this question wants me to find the position vector of P, right? So let's do this. So AP as a vector equals to black, right? So let me just label A, P, and M equals to AM, right, which is the black vector up here, plus the green vector, which is MP. Now, MP is this long thing, but because 45 degrees is given as alpha, hopefully this cleans up. So let's see. Now, just to write this as P minus, so this is almost like P squiggle minus A squiggle, which is actually Z, right? That's the complex number represented by that. That equals to AM. So let's put in AM as MP equals to AM, right? So this guy's the same thing. This guy into here. No, wrong one, sorry. The one above it. No, AM was pink. Oh no, it's just this guy. Just this guy here. He's just half of the pink, right? So half W minus Z plus, now this guy is just this guy with 1045. 1045 is 1, so it'd be like half I W minus Z. Yeah, and then I need to make P the subject, right? So I throw the Z over, and I'm hoping that everything sort of simplifies, right? Let's see. Yeah, let's see. So it'd be like, I'm just gonna rainbow everything as well. What's my answer? Oh, my answer wants everything in a half. But let's see, when I bring this Z over, let's see, where it was, there's a negative half Z here. If I bring this guy and collect it with this guy, it'd be positive half. So my final answer should be a half W plus Z, because it used to be negative half, because I'm plusing 1. If I factorize that all out, it should be IW minus IZ. Is that right? They're very similar. Plus, yeah, okay. I'm just going to leave it as exactly the same value, but the order, it's a bit different in the thing, but exactly the same. How's that? So guys, in this question, you just got to work through the diagram. How do you know to use SOHCAHTOA? Well, tan alpha is a giveaway there. Tan alpha, use SOHCAHTOA for tan, right? And you're talking about lengths here as opposed to vectors. So it feels like I'm just using geometry, or in this case, trigonometry, right? Vectors, this one here is a scalar rotation combination, right? We covered that last week. If that doesn't sound familiar, look at last week's video for the framework for it. And the last one there is just vector addition, right? Pretty straightforward. We're finding the complex number at P. So just had to find the position vector at P. Not too bad. Guys, next question. Next question is a bit harder, right? A bit more involved. So this is from Normanhurst, North Sydney Boys, 2014. A little bit more involved, right? I think it's fair to say sometimes the simpler the question looks, the cleaner it looks, the harder the algebra. This is 4 marks as well. So, it sort of sets the scene that it's going to be a very involved question. Let's have a look. ABC, okay, nothing there. Prove that if, so this guy's given, this guy's fact. Now, then we're proving that the triangle is equilateral. Hint, to commence, extend the lengths AC, AB, and BC to the real axis. Okay, what they're saying is, if this is a diagram here, they want you to sort of extend. They want you to extend. All right, extend this one, cut there. Maybe I'll extend it first. Just so I know where to cut. There. And then extend this one as well. Okay. Now, why did they get me to extend it? Definitely something to do with the arguments, right? Let's have a look. Now, where are these guys? So Z2 minus Z3, right? That's a vector going from Z3 to Z2. So that one there, right, is Z2 minus Z3. Z1 minus Z3. There's actually 2 of them, right? Z1 minus Z3 is from Z1 to Z3, so it's going this way. Right, and one more. Go in pink. Z1 minus Z2, so that's from Z2 going to Z3. Z1, sorry. Yep. So I've got 3 vectors at play. It's given me that that arrangement. Let's see. Now, so maybe it might be worthwhile, right? So the green, I'll let this guy. Oops, sorry, that's not green. I'll let maybe let's go pink first then. This angle here, right? Let that be alpha. Let maybe this guy here be beta. And let this guy here be gamma, right? Because in this case here, so maybe I'll actually state, I'll go, let's write it as black here. Let, can I zoom in a bit, right? Yep, perfect. Let, right, this guy here, so let the argument, that's the first one here, right? Let the argument of Z1 minus Z2, right, which is a pink one, equal to alpha. Now, should I use colors? Yeah, let's do it. Right. Let that be alpha. Let the argument of Z2, this one here, beta, Z2 minus Z3, equal to beta. And then let argument of Z, the green one, Z1 minus Z3. So Z1, Z3. Did I get one of the ordering one? No, that's right. Z1 minus Z3 equals to Z. Wait a second. Z2 minus Z3. I think I got the ordering of which one? The green one. Green one should be pointing backwards. Not that I don't know whether it matters, but it should be pointing this way. Right. Extend that a bit. Right. And that equals a gamma. Cool. Now, let the arguments equal to. So what I want to prove, right, is this is an an equilateral triangle, but we're given this fact, right? Let's call this fact, I don't know, let's call it equation number 1, right? I'll use pink. Equation number 1, because I'm going to use it, right? Now, in this case, what are we given? So using number 1 from equation number 1, maybe I just use black from equation number 1, right? If I take arguments of both, so argument of Z2 minus Z3 over Z1 minus Z3 equals to argument of Z1 minus Z3 all over Z1 minus Z2. Yeah. So feels like I'm going to split that up. You know, like when you divide arguments, you can actually subtract it, right? Z2 minus Z3 minus, and hopefully I'll get a relationship with it with the Greek letters, right? Z1 minus Z3 equals to argument Z1 minus Z3 minus argument Z1 minus Z2. Cool. Now let's see, what do I have here? This guy here is alpha. Gamma is this guy and this guy. So gamma, gamma, and last but not least, this guy here is alpha. So alpha minus gamma equals to gamma minus, oh, that's the pink, this one's beta, sorry, this one's beta. So, I don't know where this is going right now, but I might go to gamma with alpha beta. Is that what I should do? I'm just going to leave that for now, right? So therefore, beta minus gamma equals to gamma minus alpha. I don't really know what I'm going to use with it, so I'm just going to park it for now and see what else I can do. Now, if I can, I'm going to try to find something using this geometry, right? Why did they tell me to extend these lines? Let's see. Can you see now? Using geometry, right? Are you guys okay that? Let's see. Okay. So. Okay. See this angle here? I'm going to need a different color. Sorry. This is becoming the most colorful diagram in the world. See this angle here? That angle would be beta plus the yellow equals the green, and blue plus the yellow equals the green. So that guy must be gamma minus beta, right? Which means that this guy, right, vertically opposite, is gamma minus beta. Now, gamma minus beta, that's good because I have sort of beta minus gamma here, might be useful in a sec, right? So call that gamma minus beta. Now, if I can find, this is what I'm going to do, right? This is a game plan. I'm going to try to prove two angles equal. So it's isosceles, and then I'll go equilateral thereafter, right? That's the game plan. So found yellow, right? Yellow is gamma minus beta, good. Now, let's go, what color haven't I used? Let's go orange. I don't know how different that's not bad. Okay, orange, this guy here. Now, how do I get that guy? Looks like I can use, see the exterior angles here? I know that orange would equal to alpha, big outside minus gamma. Now that's good because in your diagram, you can go, right? What's this angle called? Angle ACB equals to alpha minus beta, and angle CAB equals to alpha minus gamma. Just to be clear, so that yellow there, exterior angles, and then vertically opposite. That orange there, exterior angles of the big triangle, right? Yeah, so you can see that if I sort of said that's equal to, right, from this side here, this one here, you know what? I'm going to be amazing because I have the benefit of PowerPoint. I'll move this down and go, therefore, I'll flip everything by multiplying everything by -1. So that minus that equals to that minus that, which is that, which are these two. And so therefore, angle ACB equals to angle CAB, i.e. triangle ABC is isosceles, at least, right? I'll prove it's isosceles and then go and prove it to be equilateral. Now, so how do I go about proving equilateral? So if I use, where did I start? I started with this statement here, right? I use the argument on the fact. Now let's use the modulus version. So, you know, I'll put it over here and then I'll move it later to complete my PowerPoint pack, right? So also from one, we use the argument. Now let's use the modulus. So if I modulus, maybe I'll modulus the top. Oops. Modulus the bottom. Modulus the top. Modulus the bottom. Right? Cross multiply. So I get like Z2 minus Z3. Z1 minus Z2. equals to, now that's the same one, so it'd be squared, right? Now, once you get that, right, what are we saying here? So we're saying that I just found these two to be equal, right? Now, where are they on the diagram? They're these two here. So basically, that's telling me that the modulus of the blue, right? Sorry, the blue side equals to the pink side, right? Which means modulus of blue equals to modulus of pink. Now, which one's blue again? Blue is Z3 minus, sorry, Z2 minus Z3, right? So this guy here is blue, right? Yeah, while the pink one is this one here, right? It's Z1 minus Z2. So these two are equal, right? I just proved that these two are equal, right? You go, since Z2 minus Z3 equals to Z1 minus Z2, right? Yeah, because it's isosceles, right? So you can go, because triangle ABC is isosceles, right? Therefore, let me see if I've got space. Yeah, might do. Therefore, if I just replace one of them with, maybe I'll replace the pink with the blue. So then you go Z2 minus Z1 squared equals to this guy minus Z3 squared, which is the final one, right? This is like the green one, right? Therefore, Z2 minus Z1 equals to Z1 minus Z, if I square root it. So in other words, since the blue, I made the blue squared equals to the green, so this one's the green one, right? So I've proven that blue equals to pink, right? That because it's isosceles. Now I'm proving that blue equals to green, right? Which basically means blue equals pink, blue equals green, all three are equal. So therefore, you can conclude triangle ABC is equilateral. So in this question, equilateral, the trick is to prove two sides equal first and then deal with the third one thereafter. And it all stems from using the fact that they gave you that ratio of, in the blue there, using the argument statement and then using the modulus of the statement, right? That's the trick to unlocking this question. Hopefully that's okay. That was a hard one, right? Guys, I've got one more question. And I think sometimes in complex numbers vectors, the hardest questions are those without diagrams. So let's do one, right? Just to really see what it's about. So this question from North Sydney Boys 2016, R is a positive number, right? Good. Then one complex numbers. Show the points which represents Z1, Z2, this guy, form the vertices of a right angle triangle. Now, right angle triangle. If this was coordinate geometry, you'll prove that the gradients are multiplied equals -1. But in complex numbers, one of the most common ways to prove right angle triangles, right? So one of the most common ways to prove right angle triangles is to prove that the argument in between here, right? Let's say, for example, this was, Z, and this was W. If you can prove that the argument of Z minus the argument of W equals to 90 degrees, right? Then you're sweet, right? That is the point. So, in other words, if I can prove that is equal to 90 degrees, then I'm sweet. Another way to say this is, if I can prove that another way to sort of prove this together, right, is that if I can prove that the argument of an expression, right, let's say this expression here, right, oops, it's supposed to be a highlight, right, has an I in it. It might be like 3i, argument of 3i, that equals to 90 degrees. In other words, right, if I can somehow find the argument expression for the triangle, right, for two of the sides, right, and so they combine them and prove that algebraically equals to something I, then I'm sweet. So in this question, if I was to draw, I'm just going to randomly draw, let's see, show that the points on it, just three of them, right? So, okay. Yep. So 3 points on that, yeah. So let's go, this is, maybe I'll call this one Z1, this one Z2, and the third point here, this guy here, Z1 minus IR Z2 over 1 minus IR, right? Now, I want to prove that this guy's right angled, right? I drew it non-right angle on purpose, but I need an expression for this vector and I need an expression for this vector, right? So maybe I'll call this one Z, this one W, right? For now. So in this case, Z equals to top minus bottom, right? Minus Z1. Oops. Goes to Z1 minus I R Z2 all over 1 minus IR. Right, as always. So this vector here is that minus that, right? While W equals to same thing, but Z2 minus 1 minus IR Z2 all over 1 minus IR. Yeah. Now, what do I want to prove? I'm going to find the arguments of both of those, right? And I'm hoping that when I subtract it, right? When I subtracted the algebra and then I put it together, right? Because basically, if you're starting with this, then this guy should be Z on W, right? Yeah. So this is the game plan. Now, then actually, before I do it, do I want to clean this up? Yeah. Let's clean this up. Our common denominator. All right. I wonder what it gives me. Say 1 minus IR times this up with Z1 1 minus IR minus 1 minus, no, this is my bracket there, IR Z2. That actually clean up, let's see. Yeah, Z1 goes away. And then there's IR Z1. All right, looks pretty clean. IR Z1 plus IR Z2, so it's like IR Z1 minus Z2. No, plus. Over. Yeah. Is that right? I feel like I got the negatives wrong. Let's see that again. So this guy is the third one. Yep. So Z1. So that minus outside here minus that's plus, is it? I don't think so. I don't think it's a plus. It should be a minus. Z1 goes away. Oh, this guy's minus. So it's Z2 is positive. Okay, cool. Close one. Be careful, because the first one's minus, right? So it's like Z2 minus Z1, like that. Think, check, quick check. Yep. This one here, common denominator. What do I get? Just be careful here. R Z2 minus I R minus. So that's Z1. This one here, Z2 minus IR plus. Okay, so in this case, the IRs cancel out, and I get Z2 minus Z1 all over 1 minus IR. Okay, so if I wanted to go now, the angle in between, right, is given by argument of Z minus argument of W, which equals the argument of Z on W. So I'm going to sub this into Z and then sub this into W. All right, it's a big fraction, but you can see that it's going to clean up quite nicely, right? So that equals to argument of IR2 minus Z1, 1 minus IR That's green, and pink is Z2 minus Z1 all over 1 minus IR. That's pink. Now, are you guys okay that that cancels out with that cancels out with that, right? So then this equals to argument of IR. R's a number, right? That's like 3i. So then I can say, therefore, that equals to 90 degrees. Yeah, therefore, right angled triangle. Is that okay? So that one there, a bit harder because there's no diagram. And it's a bit harder when they sort of give you very little guidance, but they want you to prove that they're the vertices of a right angled triangle. Algebraically, the argument of any number I, right, means that it lies on the imaginary line. In fact, it lies on the imaginary axis on the positive side, so it's 90 degrees. Guys, I'm going to leave the video there. Hopefully that was useful. A few vector questions that can be a bit harder than your usual. If you like that, give us a like, give us some comments. Let us know if there's any topics that you want me to deal with. Otherwise, I'm just going to continue on with complex numbers, but maybe change up vectors for now. Like instead of doing vectors, maybe I'll do things like roots of unity, right? Some which falls under the complex numbers part 2 branch of the syllabus. Guys, I'll see you guys in the next video.